All right. Hi, everybody. Thank you for making it. So today it's our pleasure to have Sikhar Patranabis from IBM Research India, and he'll be presenting his work on basically encrypted join queries.
Yeah, thanks for the introduction. Yeah, thanks very much for having me here, and apologies for not being able to make it to the talk last week, but good that we got there now. So yeah, so this is joint work with Charanjit from IBM Research USA. So yeah, currently Charanjit and I are part of the same organization, but while we were working on this, we started it while I was still a postdoc at ETH Zurich, and then we continued while I was at Visa Research USA. So yeah, so this is efficient SSC for join queries, and maybe I'll begin with a little bit of background. So yeah, so the motivation for this work is basically outsourced storage and processing of extremely large databases that cannot be really stored and processed locally, and so we need to outsource them to cloud servers. So for example, consider a situation where there's an organization that has a database of maybe employee records or something like that, and at some point of time, they need to basically make some amount of information available to some external auditing agency. So a pretty straightforward solution would be to outsource this database to some third-party cloud service provider, and then the auditing agency can just issue the query requests that it's supposed to or allowed to issue, and then can just get back the results. And so basically in the process, the storage and computational capabilities of the cloud server get used. Of course, this would be a very straightforward solution, provided that the organization actually trusted the cloud service provider to respect the confidentiality of its data. But in today's world, that is not necessarily the case. And so very often clients do not trust the cloud service provider to necessarily respect the confidentiality of the data. And so this basically motivates a class of cryptographic solutions, which can be broadly classified as computing on encrypted data, where the idea is that the client basically encrypts the database before offloading it to the cloud service provider. And it should be possible to actually issue query requests that allow directly computing on top of this encrypted database without decrypting it first. And so, this problem has actually been studied for a while in cryptography. So, of course, one of the, I would say, the most defining features of this problem is this, a trade-off between efficiency and leakage that we typically see in all the solutions. Whereby efficiency, I mean that, how close is the solution in terms of performance and storage requirements and overheads as such to searching over plain text databases. And by leakage, I refer to the information, potentially sensitive information that an attacker might learn. In this case, throughout this talk, we'll consider the attacker to be the cloud service provider. And so an ideal solution would be one that would be very efficient in the sense that it would be very, very close to, in terms of performance to actual plain text searches, while also leaking very little information to the attacker. But in practice, it's very hard to realize such an ideal solution. And the spectrum of solutions that we have for computing on encrypted databases, they typically lie at two broad ends of the spectrum, right? So we have very elegant cryptographic solutions like fully homomorphic encryption, functional encryption, oblivious RAM. So these are very elegant and they support computing a very wide variety of functionalities on top of encrypted databases. But as of today, they are not very efficient, although there has been a lot of research in particular on making both maybe FHE and ORAM efficient in recent years, but still they do not scale as efficiently to extremely large databases, let's say. And then at the other end of the spectrum, we have solutions like deterministic encryption, order preserving encryption, more generally property preserving encryption, which basically they are sort of, I would say, motivated or inspired by database techniques, and they are very efficient and they can scale to extremely large databases. But over the past several years, many of these schemes have actually been broken extensively by leakage abuse attacks, and so the security of these schemes is, sometimes not very well understood. So, where does searchable symmetric encryption lie in the spectrum? So it lies somewhere in the middle. So searchable symmetric encryption attempts to achieve some kind of a trade-off between security and efficiency, in the sense that it tries to be more efficient than the schemes on the bottom left, while also being more secure, or at least not being broken by as easily broken by leakage abuse attacks as the schemes on the top right. Of course, there are a few competitors to SSE in this field, which have, I would say, similar goals. So, for example, one class of, I would say, encrypted database search schemes, they rely on trusted hardware or trusted execution environments. For example, with the advent of Intel SGX a few years back, a number of works have actually, explored how it could potentially be used to securely search over encrypted databases. Of course, I actually made this slide a while back. So Intel SGX, of course, has been deprecated in a few consumer processors since then. But nonetheless, it's interesting. These classes of solutions, they basically assume a trusted hardware, and then sometimes the amount of crypto that you actually require is comparatively less here. And then, of course, there's also multi-party computation, but the solutions within this box have slightly different goals and models as compared to MPC, because in MPC typically we have various parties which have their own inputs, and then they attempt to jointly compute a function of these inputs. Whereas most of the solutions within this box, we are basically assuming that there's a client and there's a server, and the database is sort of offloaded to the server entirely, and then the computation happens at the server. So the client is typically resource constrained and doesn't want to do a lot of computation. So that's more or less the setting. And then, so this is basically a one-slide summary of what searchable symmetric encryption is. I'm sure people in the audience are familiar with it, but maybe it's good to recollect. So we basically have a client, and for simplicity, we just assume that this is maybe a single reader, single writer setting. So the client is the entity who owns the database and also is the one who's is making queries and also maybe updates the database. And then the client basically offloads an encrypted database to the server, which we assume is honest but curious, which basically means that the server is not trusted, but it does not maliciously deviate from the protocol. It performs the protocol as it is supposed to, but it tries to learn information about the client's data and the client's queries. And so typically the client stores a cryptographic key, which should be small ideally, so that it's easy to store and protect. And using this key, the client can issue query tokens and learn the corresponding response. This query could be a search query, or for example, it could be an update query. So that's a very high level model of SSE that we consider for this work. And typically SSE has been studied for many different kinds of databases. The most popular ones are typically document collections and relational databases, but some works have also looked at graph databases. So in documents, we typically assume that there's a collection of documents where each document is tagged with keywords, and the kinds of queries that we like to sort of issue over these, such encrypted document collections are either Boolean formulae over atomic equality predicates over these keywords, and also some range queries over keywords. So these are typically the kinds of queries that have been addressed. For relational databases, we have tables with records, where each record has basically a collection of attribute value pairs. And again, similar to document collections, we also have Boolean queries over attribute value pairs and range queries over attribute value pairs. In fact, most SSE schemes typically use a representation that can be used to abstract out both document collections and relational databases. But one class of queries that we typically see in case of relational databases, and maybe is not that relevant for document collections, are join queries across tables. And that will basically be the focus of this talk. And maybe just before I move on, for graph databases, we typically have collections of nodes. We have edges connecting various pairs of nodes, and then there are different kinds of queries that with slightly different semantics that we typically have over graph databases. So yeah.
So just a question, Sikhar, like before you move from this slide, like just for me to understand, like here, this slide is about how you view a relational database as you basically like you view a relational database as a collection of documents in some sense, because
yes,
instead of thinking of a document, you think of a row in a table as a document in some sense. Is
yes,
this
exactly.
is this correct?
Yes, that is correct. Yeah. So yeah, throughout this talk, I'll typically try to talk mostly about relational databases, but what you mentioned is absolutely correct. So, for example, in the paper, we typically treat records as documents and attribute value pairs as keywords. Yeah. So yeah. So any other questions? Okay. If not, then let's move ahead. So. So this is basically the outline for the talk. So I'll begin with a little bit of background on equi-joins, which is basically the functionality that we support in this work. And then I'll give a brief overview of our main construction, which is this join cross tags. I'll go into some technical details and briefly touch upon the leakage analysis of JXT. And then I'll end with some summary and open questions. So yeah, during the talk, please feel free to stop me at any point if you have questions. So I'll begin with a little bit of background on equi-joins. So this is just a simple toy example of two tables in a relational database. The first one is a transactions table, which basically has 3 columns or 3 attributes and 5 records. Similarly, we have a merchants table, which also has 3 columns or 3 attributes and 5 records. So now, as you can see, these two tables basically have a common attribute, which is transaction ID, and this is the attribute over which we would like to, process joins of join of this table and then query the join. So this is, this particular attribute we'll refer to as join attribute throughout the talk. Okay. And so let's see what is an example of an equi-join query. An example of an equi-join query could be something like, select the records or the pairs of records in each table from the join of these two tables, where the join is done with respect to transaction ID, where the date of the transaction, let's say, is January 2022, and the merchant name is okay. And as you can see that there are basically 2 records across each table, or 1 pair of records, which is T5 and M1, which would basically satisfy this query. Okay. So of course, this is a toy example. So we only have like 1 attribute other than the join attribute in each table. But of course, in general cases, you can have a very large number of attributes. But for ease of exposition, I'll just use this example, throughout the talk to give an overview of our techniques. So what we basically propose is a practically efficient SSE scheme that allows you to evaluate equi-join queries over pairs of encrypted tables. So, you can basically execute queries of this type that I just discussed. And some of the features are that one of the most important features of this work is that we do not actually do any pre-processing of joins at setup. That is, when the encrypted database is being generated or the tables are being encrypted, we do not actually do any pre-processing or any pre-computation of the joins over these tables. Okay. So what this means is that tables can actually be encrypted and added to the database independently. Okay, so as long as 2 tables have a common designated join attribute, we are able to perform join queries over these tables. We don't require these tables to be present in the database at setup at the same time, basically. So that's the first feature that we have. The second feature that we have is that the storage overhead that we have for a particular encrypted table is T-fold if the table has T designated join attributes. Okay. So this is basically, the storage overhead is not very large if the number of potential join attributes in a table is small, which is often the case in real databases, basically. And I'll talk about this a little bit more, but what I mean by designated join attributes when I discuss the overview of the scheme. One of the other features of our construction is that we use purely symmetric key primitives. So, for example, the whole scheme can be implemented using AES. We don't use any public key operations. And finally, our scheme or JXT, in fact, the name that we take is kind of, I would say, inspired by this oblivious cross-tags protocol due to Cache and others from Crypto 2013. Which actually supported intra-table conjunctive Boolean queries. And so JXT is fully compatible with that. So in some sense, JXT basically extends the functionality of OXT to beyond just doing Boolean queries within tables, to actually also being able to do join queries or Boolean queries over joins of tables in some sense.
Yeah, sorry. So I just had a question about the storage overhead. So the scheme doesn't require any pre-processing for joins, right? So that can be done on the fly. But you're saying that the storage overhead, however, is a function of basically of your joins. So how does that work exactly? So is it that you're adding storage
basically
after
the idea, so the idea is that when a table is being added to the database, we would require that, so among the attributes for this table, we need let's say the client to specify which are the attributes that could potentially be used for join queries with other tables. So it doesn't need to be specified so for all the tables together, but when a particular table is added to the database, there are actually a set of designated join attributes for this particular table. So it only supports join queries, or it can only be joined with other tables with respect to those attributes.
I see.
And so let's say that, yeah.
So at setup time, you have to say this attribute is joinable, but you don't have to say with which other table or attribute it's going to be joined with.
Yeah, exactly. Yeah.
Okay,
and so if you have like, let's say T attributes with respect to which you want this table to be joinable, then the storage overhead will be T4. Okay. So moving on. So this is basically a sort of a very high level comparison with JXT with prior art with SSE for join queries. So basically there aren't a lot, to be honest. And so the first one is basically by Seni and Tariq, who are in the audience. So this basically requires pre-computational joins over attributes sharing a common domain. But one of the features of this work is that it supports a very rich class of SQL queries, which JXT doesn't support. So JXT basically just supports basic Boolean conjunctive queries and join queries over pairs of tables. And then there's a more recent work from SENS last year by Cash and others, which also supports join queries. And this work also requires partial pre-computational joins over common attributes. So in some sense, the main novelty of JXT is that it doesn't require pre-computational joins, etc. And of course, it's worth mentioning that property preserving encryption schemes like CryptDB also support a very rich class of SQL queries. But as I mentioned earlier, they're potentially vulnerable to leakage abuse attacks. And so one of the aims of SSE in general is to prevent or have security against these kinds of leakage abuse attacks. And JXT follows the same line of work. So right. So now I'll give a very brief technical overview of JXT. First I'll discuss some of its features, and then maybe I'll go into some more details about the techniques. As I mentioned, one of the things or one of the features that JXT has is that it doesn't require any pre-processing of joins. So for example, from the example that I mentioned earlier, so the only thing that we require is basically that the transactions table and the merchants table have a common attribute, which is the transaction ID. And at setup, the client specifies for both each of these tables individually, the transaction ID is an attribute with respect to which each of these tables is joined, right? And so as long as that happens, so basically they need to be configured to support joins on transaction ID. Apart from that, we don't need any kind of pre-processing that involves both these tables simultaneously. So all the pre-processing or all the setup processing that happens will happen individually for each of these two tables. And so as I mentioned, so one of the requirements that we have, and this is in some sense a limitation of the scheme, is that we require a designated set of join attributes at setup. For example, suppose that you have a universe. So more generally speaking, suppose you have a universe of 10 attributes, and let's say table T1 is configured to support a join over attributes 1, 3, 5, and 8, whereas table T2 is configured to support joins over attributes 2, 3, 7, and 9. Let's say. So so we'll be able to support queries over join of T1 and T2 with respect to A3. So we'll be able to do this without any sort of dedicated pre-processing of T1 and T2 specifically with respect to A3, let's say. So we may not even know ahead of time, for example, when T1 is being created, that there's another table T2 which is also joinable with respect to A3, because T2 may not have been created at that point. So of course, now one question could be that is it okay to assume that there's a designated set of join attributes? So one thing that typically happens maybe in relational databases, although I'm not a database expert, is that typically the candidates for join attributes are typically small. So most of the useful kinds of queries, they typically have join attributes where the attributes are either some kind of primary or secondary key. which typically means that they have a unique value for each record, or a very high entropy attribute, which means that they have unique values for almost all records. Of course, you could define joins over attributes that are low entropy or over arbitrary attributes in general, and that's not something that JXT supports. But as long as the number of candidate attributes for joins are small and sort of can be pre-designated at setup, then JXT works with low storage overhead in some sense. So if we compare it with schemes that actually do explicit pre-processing of joins, then JXT has some advantages. One of the advantages is that it avoids certain storage blowups due to explicit join computation. So for example, suppose you have a scenario where you have a table T1, which is tall and skinny, so it has many records and few attributes. And then table T2 is like short and wide, so it has few records and many attributes. So then their equijoin for any given common join attribute could be tall and wide, right? Which means that there's a massive blowup in storage. And this is something that JXT explicitly avoids when it creates the encrypted database, because it doesn't compute these equijoins explicitly. The other thing is that it also avoids recomputations of joins in certain scenarios. So for example, suppose that there's a scenario where table T1 needs to be reset up at some point of time. So maybe that's because maybe it needs to be updated in some form, or maybe some data was lost and needs to be recovered, and then the re-encryption needs to be done. So one of the features of JXT is that it does not now need explicit recomputation of joins with T2 or with other tables, right? So those tables, as long as T1 has common joinable attributes with the other tables, it will continue to support those queries even after being reset up. So in some sense, different tables can be reset up independently, or if tables need to be updated at different frequencies, then they can be just updated independently, basically. So these are some of the reasons why we feel that avoiding pre-processing of joins could be useful. Of course, the other thing with pre-processing of joins is that if we pair join pairwise every table, there's some kind of a worst case quadratic storage blowup possible, which is also sort of avoided. So okay, so now that we talked about this, so what are actually the storage and search overheads? So the storage overhead of JXT is as follows. So suppose a table has m rows or records and n columns or attributes, and let's say t of these are designated as join attributes, and the overall storage requirement is m times n times t, which is basically a T4 blow up over what would be the plain text storage requirement, for example. And the search overhead is as follows. So suppose we consider the same kind of query or example query as before. And let's say that, in a more general scenario, we have L1 records in the transactions table, which is matching the first attribute value pair. And there are L2 records in the merchants table, which is matching the second attribute value pair. Then the overheads are as follows. So the communication cost is order of L1 plus L2, and we require a single round of communication between the client and the server. The computation cost at the client is also order of L1 plus L2. However, the computation at the server is actually multiplicative. So it's basically L1 times L. And so this is something that could potentially be suboptimal, and maybe there are ways to improve this. One of the reasons why we incur this cost is because we avoid all kinds of pre-processing. So in some sense, there has to be this sort of matching between all the records in transactions table and all the records in merchants table, and trying to figure out whether there's a common attribute for them, basically common join attribute value for them. So this is one of the reasons why the computation at the server for us is multiplicative. So it's a very interesting open question to see whether this can be brought down to say optimal, which would be, let's say, the size of the result set, which can be significantly smaller than L1 times L2.
So just a question that I have here, so it's not completely clear to me that storage overhead, at least for GXT, is doing much. I mean, it's better all the time compared to the pre-processing. For example, our work, and because you have this multiplicative factor of T, which is sometimes just talking complexity wise, it's not realistic wise, but in some cases it might be way more than what you could have, for example, with pre-processing, in the case where you can imagine when you have some data distribution where there are very few joins, and you will end up with not very quadratic. Quadratic is kind of like the worst case, but you should maybe have also what is the best case. And in that scenario, like MNT like will be way higher than what you would have in storage-wise compared to, for example, pre-processing. So I think that at least, like, I'm not sure like if that's correct. Like this is just on top of my head right now. Like it seems like it's not always better. Like there are cases where pre-processing is also much better than this one in some cases. So this is one. So the other one is that, so here it seems like in search overhead, like maybe I missed it, maybe you said it, Sikhar, but in competition at the client, is it like a round protocol where you need to first know how many records you have that they match and then send it back? Is it like a multiple rounds, or is it like just here is my token, send it to the server, compute, and the token is itself? I'm missing something, like, because I don't know why the token is function of the selectivity.
Yeah, so it's a single round. So first of all, to answer your first question, yes, you are right. So we are not claiming that it is always better. So it could definitely be worse depending on the kind of database that we are working with. So the only thing is that, as I said, like it basically avoids the kinds of scenarios when maybe the join of two tables is much larger than the individual tables. But of course, I mean, in the worst case, either one could be worse. One thing that, of course, JXT supports is that, if, for example, you need to reset up a table at some point of time, then you can do it independently. You don't need to recompute the joins or have a pre-processing of the joins with all the other tables. So that's something that's a feature that JXT offers. But yeah, I completely agree. I mean, the storage overhead could be, better or worse. It depends on the kind of table. Of course, it's probably better if the number of potential joins are very large. And probably worse if the number of joins is very small. The second question, yeah, so it's a non-interactive protocol in some sense. So the client just sends across a set of tokens to the server, and then the server does all the computation. And in some sense, the number of tokens that are sent across it's basically like one token for each entry in the transactions table that matches the first attribute value pair, and tokens for the merchants table, for the records corresponding to the merchant table matching the second attribute value pair.
So no, thank you. So thank you for this. This clarifies a lot. But it seems to me like the way how you use the word token maybe like is different from the way how I'm maybe thinking about it, because like for the way how I understand, like for example, token in SSE and SCE is that like you just one query, and the database, I mean here in this case, will take care of generating all of the whatever it needs to do the computation. But here it seems that you like the way how you use the word token is that like you send a token for every possible match on T1 and in T2. So in total, you kind of like you have L1 plus L2 sub tokens. And for me, this is like, I view this as one token actually. And this is why I was thinking, okay, like the token is okay. And this doesn't need to be interactive, right? You said that this doesn't,
yeah,
like you just send L1 plus L2. Okay, makes sense.
Yeah,
okay.
Thanks. I mean, yeah, that's actually a very good way of putting it. So yeah, so it's like L1 plus L2 sub tokens, which are part of this larger token essentially. Yeah. So and the other thing is that JXT is compatible with OXT. So in particular, OXT supports intra-table conjunctive queries. So with OXT you could potentially do, so suppose a situation where transactions table and merchants table had maybe more attributes, and then you could actually do some kind of intra-table conjunctive queries with OXT. And so one of the things that you can do is you can combine OXT and JXT to support more general conjunctive queries over joins of tables. So for example, you could now have a query over the join of table 1 and table 2, where you have a conjunction of two attributes from attribute value pairs from table 1 and a conjunction of two attribute value pairs from table 2. So these kinds of things can also be done without increasing the number of rounds of communication. And that's mainly because JXT in some sense is structurally and also in the manner in which it generates the tokens from the client to the server is very compatible with OXT. So that's another feature of JXT, and also one of the motivations for our design frame. So in some sense, JXT complements and extends OXT to support a richer class of SQL queries in some sense. Okay, so that was more or less the overview. And so now I'll probably try to, in the time that is remaining, I'll try to give an overview of some of the techniques that we used. And I'll basically use the same toy example. So, just to recap, so we have these two tables, and we saw an example of an equi-join query on these two tables. So at a very high level, so what basically I'll try to keep the math as simple as possible. So basically what we require is just a PRF family. So that's all we require. So we just use a pseudorandom function with different keys. And in order to make the notation simpler, I'll not explicitly mention the keys. Rather, I'll use these small case letters, so little f, little g, and little h0 and little h1 to denote the PRF being used with these keys. And I hope that this simplifies the representation somewhat. So at a high level, the idea is the following. So basically what we want, what we define are these two terms, or three terms rather, which are these x, y, and z terms. Okay. So the x1 term is basically an evaluation of the PRF with the first key on the identity of a record, and just the attribute, the join attribute name. So it doesn't explicitly specify the value, but it just specifies the join attribute name. And the second term, which is basically the y term, is the evaluation of the PRF with a different key, but this time on the join attribute value pair. So this is something that is that is specific to the particular value that the join attribute takes for this particular record. And then we define a term z, which is basically just simple bitwise XOR of these two PRF computations. Okay. So basically, I'm assuming that this PRF just takes any bit string as input, and then you can think that all these inputs to the PRFs are just represented using whatever, some kind of bitwise representation. So these are three terms. I'm not saying that this is explicitly how it works, but these are three terms that we'll revisit later. So these are three terms that we use. And they'll be computed, but they'll be used in some form. So they won't be used directly, but we'll be using we'll be building on top of these terms basically. So this is something that we'll have, and this will have for basically each record, and basically the corresponding value in the join attribute for the join attribute. So basically we'll have something like this for the first record. We'll have a corresponding thing for the fourth record and also for the fifth record, for example, right? So, but they're all computed in the same. And then we'll do a very similar thing also for the merchants table. Yeah, so I'm going to use this prime in the superscript to denote things that are for the merchant table, but they don't mean anything different. I'm just using them to designate the fact that the non-prime variables correspond to the transactions table, and the prime variables correspond to the merchants table. So now, yeah, so similarly, we have x prime, y prime, and z prime for each record in the merchants table. So this is an example of what it would be for the first record. And similarly, we have something for the fourth record. This is a little typo, so it should be like 4. And so interestingly, one thing that we observe is that if we look at the transactions table and the merchant table, and we look at the pair of records that actually match, which means that they have a common a value in the join attribute, which is transaction ID. So we'll see that basically they have their own x and z values, but the y value is essentially the same. And this is something that we would like to exploit in order to be able to identify for various pairs of records from the transactions table and the merchants table, whether they have the same transaction ID value at a high level. And so, yeah, so this is the one observation that we'll rely on, is the fact that y5 is equal to y prime 1, for example, in this case. Okay, so this is like a very sort of high level idea that, okay, we have a set of terms for the records in the transactions table, we have a set of terms for the records in the merchants table. But then the question, of course, is that we want the server to be able to recover either these values or some version of these values, maybe masked with something. So how exactly do we want to organize the data structures that we store at the server, right? And so, okay, and maybe before I move on, it's worth mentioning that if we have a pair of records that actually don't match. So for example, it's interesting to look at T4 and M4, because T4 and M4 individually they satisfy the attribute value pair for that particular table. So for example, T4 also has the date as January 2022, and M4 also has the merchant name as Apple, but they don't have a common transaction ID, and so they're not a valid output of the join query. And so basically in this case, if you see the Y values are actually different, right? So they're basically completely independent, pseudo-random. So this is basically the feature that we somehow want to exploit. And so just taking a step back, we want to individually process the matching records in the transactions table and the merchants table, and somehow figure out whether they have a common join attribute. And so the way we do that is basically for each table, the server basically stores a key value store, which basically has entries of the form key value in some random order, and given a valid key, the associated value can be efficiently retrieved. So I'm just going to use this very, very generic and abstract data structure. Of course, there are many ways to instantiate this in the SSC literature. There's tset, which OXT uses. There's encrypted multi-maps. So I'm just going to use a very sort of generic and abstraction, which we'll refer to as a key value store for simplicity. And then, so this basically data structure will have an entry corresponding to each of the records, or in this case, it has a single entry corresponding to each record, but more generally speaking, there'll be basically multiple entries corresponding to each possible join attribute. So in this case, there's just a single join attribute, so there's just one entry for each record, and I designate by red the entry corresponding to the last record, and by green the one corresponding to T4. And so what actually are the values stored here, right? So we want to basically store some function of the X and Y values that we just saw, but not immediately in the clear. So there are some reasons why we don't want to store it immediately in the clear. For example, if we store the Y value in the clear, it would immediately leak that maybe two records had the same transaction ID. So that's something that we don't want to leak. And similar information could also be leaked by the X value. So what we do instead is we mask this by function of the attribute value pair corresponding to the date field. So for example, for the record T4, we basically have an evaluation of the PRF H0 and an evaluation of the PRF H1 masking the X and Y values. And how do we evaluate this PRF? Well, we basically have the attribute value pair itself along with a counter, which basically increases for every occurrence of that particular attribute value pair. So for example, in this case, date, there are two entries corresponding to it, which are matching the attribute value pair date and 1st of January 2022. So we have two entries here, one with counter 1 and one with counter, right? And so basically, these are used to mask the corresponding X and Y entries. So this is what we basically store as the value in this key value store. Okay, and so we do a similar thing for the merchants table as well. So for when we are processing the merchants table, we would similarly process the attribute value pair merchant name equals Apple, and again there are two entries which match this. And so the first one basically which is marked by red would basically mask the corresponding X and Y values, and similarly the second entry would mask the X and Y values corresponding to the fourth record. Basically.
So Sikhar, sorry, I think I missed something at some point. So how do you choose these attributes to mask, like merchant or date? That like
right. So basically we do this for so this is very similar to what we would do in a normal, let's say a simple SSE for single keyword search. So you would do this for every attribute value or like every keyword, right? So for every attribute value pair, you would see the records matching it. And then you would basically mask the X and Y values corresponding to that particular record and that particular join attribute value with the corresponding counter. So you would do this for every attribute value, essentially.
I see, for every attribute.
Yes,
okay.
Yes.
And what if my table is just like a transaction ID?
So if the table is just a transaction ID, then so in that case you would basically just do it for transaction ID itself.
But
right.
what what other attribute do I use to do the masking? Like, let's say that I wanted to do joins on transaction ID, but my table is just like, basically the only other column is transaction ID. So would I use, I guess, the ID? I would use the primary key to mask in that case?
So you would just use, so the age values you would evaluate on each attribute. So you don't treat the join attributes differently from the other attributes in this case. So in that case, you would just do it for, so you would evaluate both H0 and the X and Y values for transaction essentially.
Okay.
So the X and Y values are computed. So the X and Y values are specifically computed for the join attributes,
right?
And the masks are computed for every attribute, including the join attributes.
I see. Okay. Oh, including the join attributes. Okay. All right.
Yeah.
Thanks.
That's basically what I guess I mentioned here. So the server stores this masked X values and masked Y values for each tuple, tuple of the form record, join attribute, attribute value pair. So for every attribute value pair, you would basically look at all the records that match this attribute value pair, and you would store an entry for each record and each join attribute. So for example, here we only have one join attribute. If you had multiple join attributes, then you would store a separate entry for a separate masked X value and a separate masked Y value for each join attribute. And so this is basically what contributes to the t-fold overhead in our case, right? Because for every join attribute, you would basically do this. You basically have one could think that for every entry in the table, you are basically storing t values essentially. So that's how the t times overhead works. And then of course, for any attribute value pair, the client should be able to generate sub tokens that allow the server to basically retrieve the relevant entries, the relevant masked entries. And this can be realized using already existing techniques in SSE literature like t-set or encrypted multiplexers, as I just mentioned. So this is the first data structure. And then, okay, so we talked about the X, Y, and Z values. So we know that we are storing the masked X values and the masked Y values. The only remaining thing is the Z values. And these basically the server stores directly. So there's no masking there. It stores them directly in a Bloom filter, any other data structure that allows efficient membership testing. So it doesn't need to explicitly store these values. It just needs to record their membership. And this is also, again, very similar to the cross-set data structure that is there in the OXT protocol, for example. So at a high level, we have basically two data structures. We need something that resembles a key value store. You could realize it using an encrypted multimap, for example, and for the masked X values and the masked Y values, and then you store the Z values directly in this Bloom filter data structure. And okay, so now let's see how search works using an example. So for example, let's recap a little bit. So we talked about these X values and Y values. And now suppose that there are a pair of matching records, right? So there's a record in the transactions table and a record in the merchants table that matches, first of all, the actual attribute value pairs that are queried, which are date and merchant name, and they also have a common transaction ID. Now, in this case, the Y values would basically be identical, and this is something that we would rely on. But note that the server, right, when it searches for let's say date on transactions table and merchant name and the merchants table, it would not get the raw values of X and Y. Instead, what it would get are basically these masked values, right? So it would basically be able to recover the masked X5 and Y5, and it would recover the masked X prime 1 and the masked Y prime, right? Now, interestingly enough, what happens is that since Y5 is equal to Y prime 1, we can also replace Y5 with Y prime 1 on the left, right? So, so basically we have the same Y prime value, which is masked by two different age values on the left and on the right, right? And now basically, if we ignore the H0 value for the transactions table and the H1 value for the merchants table, and just focus on the H1 value for transactions on the left and H0 on the right, we see that we basically actually have a relationship here. So we have x prime 1 and we have y prime 1, and z prime is basically nothing but x prime 1 XOR y prime 1, right? But what we have is we have these two additional masks, right? But note that these masks are just functions of the attribute value pairs that are part of the query, right? And so what the client can actually do is the client can basically send the XOR of these two masks additionally as subtokens to the server. So the client can send to the server subtokens which allow it to recover the masked x prime and y prime values. It can also send to the server the XOR of these two masks. And what the server can do is it can XOR everything, and then it would basically recover the z value, and it can just directly check its membership in the Bloom filter. And if these two records have a common join attribute value, then the Bloom filter membership would return true. Okay, and that's when the server would know that, okay, these are a pair of records that individually they satisfy the corresponding attribute value pair in each table, and they also have a matching join attribute value, right? Now let's see what happens, for example, if they don't match. So for example, let's consider this pair T4 M4. Of course, there are other pairs we could consider, like we could consider T5 and M4, or we could consider T4 and M5 M1 as well. But let's just consider T4 and M4. So in this case, the y values are pseudo-random, so they are completely sort of, at least computationally, they are uncorrelated. And so now what happens is that when the server recovers the masked x values corresponding to these entries, right? It actually is not able to recover the z value. So that's the overall idea. So the idea is that since the y values don't cancel because they are not the same, so there is no way in which the client is basically the server is able to recover any matching z value. So for example, what happens here is that the client sends to the server the same things that it sent in the first case, right? So the server can still recover the masked x and y values, and it also gets the XOR of the masks. But when it computes the XOR of the masks and XORs it with the masked values, it basically recovers something that is not in the Bloom field, right? And so in this case, the membership test essentially returns false, and this indicates to the server that, okay, these are a pair of records that don't have a common attribute, that don't have a common value for the join attribute, essentially, at a high level.
Hi, I had a quick question about how the server tokens are generated.
Mm-hmm.
So actually I have two small questions relating to that. So one is this concatenated 1 and the apple concatenated with the 2. Those numbers appended to the end are generated using a counter when at setup. You mentioned. Is this counter restarted for every table, like so that the counter is reset? Okay. Secondly, in order to generate these tokens, is there some sort of like client side information that has to be stored?
Yeah, so right. So yeah, that's a great question. So yeah, so first of all, yeah, the counter is basically restarted not only for every table, but also for each attribute value pair in each table. So basically it's a unique counter that exists for each attribute value pair. And yeah, of course it's different for each table. And yeah, the second question, yeah, the answer is yes. So basically, typically in many SSE schemes, we typically assume that the client stores some amount of a local state. For example, one of the things that it typically stores, sometimes this is assumed, is that the frequency of each attribute value pair. Of course, this does not necessarily need to be stored, in the sense that there are works that have explored how to avoid this storage. One possibility is to actually also store this in an encrypted way on the server, and then fetch this information as and when required. The other option is to basically not store the counter at all, but just go on sending tokens until the server basically sends an invalid response, because you basically sent you are hitting a key value pair that doesn't exist, for example, in the table. So yeah, there are possible workarounds, but yeah, in the simplest form, I would say that yeah, you assume that the client stores the frequency of each attribute value pair in each table.
Okay, thank you.
Sorry, I had one follow-up question then, because you're saying that I was wondering that because the counters are reset for every table as well as attribute value pairs. So is it possible that masked Y values are then the same if the two tables also share, two columns which are same other than the join attribute? For example, let's say the second table T2 also had a date column with this date.
Yeah, so that's a very good point. Yeah, so typically, what we would assume is that so one way of avoiding that is to basically just also include maybe the table ID as an input to the PR. So that's one way of avoiding that. Yeah, so that's actually a very good point. So yeah, that's something that I skipped here for to keep the thing readable. But yeah, that's something that you would typically do. So the counter, for example, you can think of it as it's of course being reset, but maybe the counter is also appended with something that distinguishes tables from each other. Yeah, does that answer your question?
Yeah, sorry. Thank you. Yeah.
Yeah, sure. Okay, so maybe yeah, quickly moving on. So yeah, so one of the things that you might have noticed here is that right now we are assuming that the client is basically sending to the server these pairwise XOR of the masks. And of course, this would mean some kind of multiplicative overhead, not only in terms of communication, but also in terms of computation at the client. So in the paper, we actually propose some additional optimizations where the client doesn't actually send the XORs of the masks, but can actually send these masks themselves individually. But it requires some more some additional small additional masks to be used in order to avoid leakage. Because if you just send instead of sending the XOR of the masks, if you send the masks individually, then in some sense, the server can actually use these individual masks to infer some more information across queries. And so there we have some additional mechanisms to and optimizations to reduce this particular overhead to linear, so that the client doesn't actually have to do a computation for every pair of records from first table and the second table. It can just do a bunch of computations for the first table and a bunch of computations for the second table. So yeah, so I don't have time to go into those optimizations. So yeah, I'll refer to the paper. One thing, of course, is that the overhead of the server does remain quadratic. So the server still has to do a check, the check memberships in the Bloom filter for every record in the first table and every record in the second table that match the corresponding attribute value pairs. So it still has to do a pairwise testing. This is something that we tried to avoid, but we could not. So this is a very interesting question as to whether we can somehow reduce this overhead from quadratic to something that is closer to maybe the result set essentially. But yeah, we couldn't do it. So yeah, I'm very happy to discuss if you have any ideas on how the overhead of the server could be reduced. Right. So, and maybe I just wanted to mention quickly, and that JXT can also be extended to the multi-client setting in pretty much the same way as OXT can be extended. And in this case, of course, instead of using simple PRFs, you would need oblivious PRFs and oblivious PRF-based protocols. So, but JXT it is possible to extend JXT, and of course, JXT also has a single round of communication between the client and the server, which is typically good for the multi-client setting. And the other thing is that we also discussed some extension in the paper, some extensions to JXT where maybe the tables are not they're still sort of under the same authority, so they're still encrypted using maybe the same key, but they may be owned by different entities and may be stored at different servers. And so, for example, it could be the case that entity 1 owns the transactions table and entity 2 owns the merchants table, and they could be like sort of mutually distrusting. And so the way JXT is sort of constructed, because the way in which the tables are set up is also completely independent, and also the set of tokens that the client sends corresponding to each table are also sort of, you have a set of individual sub tokens for the first table and a set of individual sub tokens for the second table. So JXT can also be adapted to support these kinds of scenarios. So we didn't propose a concrete protocol for this, but we believe that it should be possible to adapt JXT to these kinds of scenarios. Of course, it remains to be seen whether such scenarios are very well motivated. But it is possible, for example, that maybe two different organizations have two different tables and they intend to compute a join over their own tables, but they're not going to trust each other, basically. And so in these kinds of scenarios, JXT can be adapted. Okay, so finally, I just wanted to briefly mention about the leakage of JXT. So, for example, what the example that we considered, I guess one thing that you must have guessed by now is that it actually leaks the individual frequency of each conjunct. So it would leak, for example, the number of records in transactions table that matches the first attribute value pair, and the number of records in merchants table that matches the second attribute value pair. And secondly, because of the nature of the data structures that are typically used to implement these key value stores, it would also leak the equality of these conjuncts across queries. So of course you could use additional mechanisms to hide that, but both the frequency, you could use like volume hiding EMMs, for example, or other kinds of techniques that might be able to hide equality pattern or query pattern, for example. But in its basic form, it leaks these things. And if you wanted to hide them, then you would have to use additional techniques. And but there is one particular leakage that's actually very specific to JXT, and this is not something that is seen in OXT, for example, is this join attribute distribution pattern leakage. So one of the things that happens in JXT is that it leaks the frequency distribution of the values taken by the join attribute across records in the first table, right? So for example, suppose that transaction ID, for example, is the join attribute for the first table, and it basically leaks the frequency distribution of values that are taken by it across the records matching the first attribute value. Now, this is not very serious if the join attribute is already a primary key or a secondary key, because in this case, the value is unique for each record. So really, there's like every value occurs only once. This could be a non-trivial leakage if the join attribute is low entropy. And so we leave it as an open question to analyze the impact of the leakage in that case. Of course, one thing is that one strategy that we propose is that if you structure the query such that the join attribute is high entropy in the first table, then you can avoid or reduce the impact of this leakage. So if there's a situation where the join attribute is high entropy in the first table and low entropy in the second, then it's preferable to structure the query such that your first table is the one where the join attribute is high entropy. So yeah, that's essentially it. So yeah, I'd like to end with some open questions. So one of the things is that can you extend JXT to flexibly support joins over arbitrary attributes, to joins of 3 or more tables? That's another open question. And extending it to maybe supporting dynamic addition, deletion of records, and analyzing the leakage even more. And one of the things that is currently we sort of didn't get to that point is actually implementing JXT and checking its performance over extremely large databases. But we believe that because it's purely symmetric key, it should be reasonably efficient in practice. Yeah, thanks. And yeah, thank you for listening, and I'll be happy to answer any more questions. Sorry, I probably went a little over time, but yeah.
That's fine. No worries. Thanks. Yeah, thanks for the great talk. Let's thank the speaker.
Thanks.
Virtual. We have maybe a little bit of time for questions. Just already over time. So I guess one thing I'm curious about is like the dynamic case. So you mentioned that, so this is just for static, right?
Yeah.
And so like, do you anticipate the dynamic case to be particularly challenging, or?
Yeah, I think, so basically, there have been some extensions to OXT I guess one of the things that would be interesting to see is what would be, like, for example, typically for dynamic databases, we would have to ensure like forward privacy and now more recently backward privacy. So it would be interesting to see what notion of forward and backward, like what would be the definitions of forward and backward. I mean, forward privacy is probably more clear, but backward privacy is like, we might need new definitions in the case of joins, because I don't think that's really been explored much. So I think that's something that's very interesting. I think it's possible to extend it. It's more like whether the notions of security that we achieve are, the correct ones, for example. I think that's something interesting to look at.
Yeah, that's an interesting point, actually. Yeah. All right, any other questions?
No, that's a great talk. Thanks, Sikhar.
Yeah.
Sure.
Yeah.
Thank you very much.
Yeah, it's a really nice game.
Sure. Thanks.
Yeah. All right. Well, thanks everybody for attending. Thanks, Sikhar, for the great talk. I guess we'll see everybody next week.
Yeah, sounds good. Thanks
Bye.
a lot.
Thank you.